Hello and welcome back to Machine Learning. I'm Jovita Christie, and in this video, I'm going to talk to you about parameter estimation. So we are going to look at three different parameters, estimations. One is known as MLE, which is maximum likelihood estimation. The second one is called MAP, which is maximum a posterior, and the third one is called Bayesian estimation. So let's begin. First, let's talk about what is parameter estimation. So parameter estimation refers to the determination of the best values of certain parameters in a numerical model through data assimilation or other similar techniques. So estimating a parameter of a numerical model, the numerical model could be a Bayesian model, a binomial model, Poisson model, exponential distribution, whatever distributions that we have studied so far. So it could be any of those distributions could be called a numerical model. So when you are, for example, for a binomial distribution, when you're estimating the probability of success, that would be an example of parameter estimation. And this is often done by data assimilation, which means you will gather data and examine the data to find that parameter. There are also other techniques to do the same. Which are the methods for parameter estimation? So we have the maximum likelihood estimation, which is also called MLE. We have maximum a posteriori, which is also called MAP. We also have the Bayesian estimation. So let's first take a look at the maximum likelihood estimation. So in maximum likelihood estimation, we wish to maximize the probability of observing the data from the joint probability distribution given a specific probability distribution and its parameters. So what we want is we want to maximize the probability of observing the data. And what is used here is the joint probability distribution for any specific distribution. And we'll see in a minute what that looks like. This is what the formal statement looks like. It is Px or P of x given theta. Theta is the parameter you want to estimate. Or it could be written as P of x1, x2, x3, so on up to xn given theta. So what you have to find out is this value of theta. A capital X is your data, so you could write capital X or you could write all the data points if you wish to. And let's take a look. So what do you have here? This result is a conditional probability. And if you find that, it is known as the likelihood of observing the data given the model parameters. And the objective of this function, this MLE, is to find the set of parameters known as theta to maximize the likelihood function, for example, result in the largest likelihood value. So find the value of theta in such a way that it is the most probable value. So you have to maximize P of x given theta. Let's take a look at an example of how you can apply MLE for a binomial distribution parameter. So let's say that there is a talent acquisition company, and this company is interested in estimating the probability of successful recruitment of top executives for their clients. And I'm going to, in a while, show you a table which contains in every cycle how many people were recruited out of 10. And what we need to do is estimate the probability of success, which is P, in a binomial distribution using maximum likelihood estimation. We know that this is a binomial distribution because there is success failure type scenario, which means there are only two possible outcomes and multiple trials. That's why. So this is the table given. The recruitment cycle number is given. So there were 8 cycles. In each cycle, out of 10, this many people were recruited. So you can say that in the first cycle, out of 10, 4 people were recruited. In the second cycle, out of 10, 2 people were recruited, and so on. So if you want to estimate the value of P, which is the probability of success in a binomial distribution, you can use this formula right here. And this formula, of course, came with a lot of derivation and stuff. We are not going to go into the details of that, but we are going to apply the formula, which is calculated in this manner. So you have sigma I equal to 1 to 8 because 8 cycles, xi, which means all these values, 4, 2, 5, 4, and so you take a sum of that, which amounts to 26. Divide that by m into n. Now, n is how many people were there in each cycle, so 10. And m tells you how many cycles were there. So there are 8 cycles. And this is how you will be doing. So you are essentially repeating an experiment m times, 8 times. So you have trials, you have 10 trials, but you're repeating those 10 trials. 10 trials because 10 people, but you're repeating those 10 trials 8 times. So if you calculate that, you will be getting 0.325, which will be your probability of success. That is how you can do calculations using maximum likelihood estimation, also known as MLE. Let's now talk about the next way to do parameter estimation, which is maximum a posteriori, also known as MAP. So this uses the Bayes theorem, which we have studied extensively in our videos. You could refer those if you've forgotten. And it uses also conditional probability because Bayes theorem is based on conditional probability. It involves calculating the conditional probability of one outcome given another outcome, and then using the inverse of that relationship like this. So you have P of A given B, which is equal to P of B given A into P of A upon P of B. This is nothing new. We have studied that before. We have seen this theorem, so nothing very new here. And the quantity that we are calculating is typically referred to as the posterior probability, which is this, of A given B, and P of A is the prior probability of A. So P of A is probability of A without knowing anything about B, but now that you know something about B and B can affect A, you can find the posterior probability. We are going to see an example in a minute and you'll understand it better. The normalizing constant of P of B can be removed in this case because it's just there to normalize the probability so that you don't get a value higher than 1. So you can show the posterior directly to be proportional to the probability of B and B given A, just like this. So you could write that P of A given B is equal to P of B given A into P of A. We don't need to divide it by P of B. We are only doing it so that we get a value out of 1 and not greater than 1. Or simply you could just write it like this, right? And this is a very helpful simplification because we are not interested in estimating a probability, but rather in optimizing a quantity. So a proportional quantity is good enough for this purpose, okay? So that's what maximum a posteriori is. And let's now talk about also the Bayesian estimation in a minute. You could relate this calculation to your desired estimate to estimate a distribution, which can be stated like this. So once again, we have theta. So P of theta given x equal to P of x given theta into P of theta. So you could use this. We are going to use this in a minute. And if you maximize this quantity over a range of theta values, then it would solve the optimization problem of estimating the central tendency of the posterior probability or of the model. So it could be any distribution model. We are going to be using one soon. This technique is called maximum a posteriori estimation, also sometimes called maximum posterior estimation. So all you have to do is maximize P of x given theta into P of theta. Now let's talk about Bayesian estimation, which is what is used to apply MAP. We are going to see an example so you'll understand it better. So in estimation theory and decision theory, a Bayes estimator is an estimator or decision rule that minimizes the posterior expected value of a loss function, and equivalently it maximizes the posterior expectation of a utility function. So of course this is the definition, but we are going to see an example to make you understand this better. So we are going to do this for a Poisson distribution. So we're going to apply it on a Poisson distribution, and we're going to take this scenario where there is a traffic control engineer who believes that the cars passing through a particular intersection, which means a crossroad, arrive at a mean rate lambda equal to either 3 or 4. Remember, in Poisson distribution, we use lambda, right, for a given time interval. And prior to collecting this data, the engineer believes that it is more likely that through that crossroad there will be 3 cars passing instead of 5. And he also has this probability, which is the prior probability of where P of lambda equal to 3 is 0.7, P of lambda equal to 5 is 0.3. Now, there is one particular day where during a randomly selected time interval, this engineer goes and checks how many cars are passing through that particular intersection, and he finds that there are 7 cars, okay? But the observations that he had made was it could be either 3 or 5, but now he has seen 7. So given this observation, now what is the probability that lambda can be 3 and lambda can be 5? So that's what we have to estimate. We have to estimate the value of lambda, which will of course be the maximum possibility, whatever is the maximum probability. So now that we have this additional knowledge that, there could be 7 cars also, we have to find the new probabilities of lambda equal to 3 and lambda equal to 5. So simply by using the definition of conditional probability, you could write like this: P of lambda equal to 3 given x equal to 7. X is the parameter that you just observed. This will be lambda equal to 3 comma lambda x equal to 7 upon x equal to 7. So what you see on top is the joint probability. And using Bayes' theorem, you could write this like this. Okay. So this is using joint probability, but we are going to use Bayes' theorem like this, which is simply inverting what you have here. So you're taking x equal to 7 given lambda equal to 3, and then you are putting P of lambda equal to 3 over here as multiplication. And in the denominator, you're going to take this whole term and add to it lambda equal to 5 and x equal to 7, because the other possibility of lambda is 5. So it can be 3 or it can be 5. So we are going to add the second possibility as well here using Bayes' theorem. And now for the calculation part, we need a couple of values here. So we require value of x equal to 7 given lambda 3, also x equal to 7 given lambda 5. We don't have these values. So to find those, we can use a table, which you can find in a lot of statistics books, and you could also search for it online. It is the Poisson distribution cumulative density table, which you can see here. So from this table, if I want to find out x equal to 7 given y lambda equal to 3, I just have to search for x over here in this side. So 7 is here. Lambda is 3, so I have to search for the value 3, which is here. So I have to go in this row and search, which is 9.88. So put 9.88. Check what is the value above that. So the value above that is 9.966. So subtract that because it is cumulative. That's why we are subtracting. We don't want values for everything from 0 to 7. We just want 7. If we wanted everything from 0 to 7, it would be 0.988. But since we just want 7, we are going to subtract the previous value and get 0.022, which is this value, x equal to 7 given lambda equal to 3. Next, for this x equal to 7, lambda equal to 5, again locate 7 here, which is here. Locate 5, 5 is present here. So I have the table in 2 parts. You could just get one table which contains everything. So this value is 0.867, which comes here. And the value above that is 0.762, which we subtract, and we get 0.105. So now that we have these 2 probabilities, we could easily solve our equation by putting all those. We already had 0.7 and 0.3. So we get this as 0.328. So our initial probability was for lambda equal to 3 was 0.7, but now it has decreased. And this is called the posterior probability. This is because it is the probability that the parameter takes on a particular value posterior to x equal to 7. So before we knew that there was going to be 7, we had taken 0.7, but now that we know x can be 7 or lambda can be 7, we can say that this is the revised probability, which has decreased from 0.7 to 0.328. Okay. Similarly, we could do the estimation for p of lambda equal to 5 given x equal to 7 in a similar way. If you do that, you'll get 0.672, which has increased. Prior probability was 0.3, but now it is 0.672 because we observed that there could be 7 cars also, which means 7 is much higher than 3 and much, compared to 5, it's not that much higher. So that's why probability of 5 has increased and 3 has decreased. So that's what you can estimate here. Again, 0.672 is posterior and 0.3 was prior. So that's it for this video. I'll see you in the next one. Thank you for watching.